Hello everyone, welcome to my YouTube channel. In this video, I am going to discuss linear differential equation with constant coefficient. So first we define what is a differential equation. An equation consists of various order derivative is called differential equation. Of course, equation means what? An expression which contains the sign of equal to is called equation. And an equation which consists various order derivative, that is first order derivative, second order derivative, third order derivative and so on. So an equation which consists various order derivative is called differential equation. For example, this expression contains the sign of equality, therefore it is an equation. Further, it contains a first order derivative dy by dx, therefore this is an equation containing derivative, therefore it is a differential equation. Similarly, this expression contains sign of equal to, therefore it is an equation, and further it contains various order derivative, first order derivative, second order derivative, therefore this expression is a differential equation of second order. Also, this expression is also consists of first order and second order derivative, therefore this expression is also a differential equation because this is an expression containing, this is an equation containing the derivative. So the definition of differential equation is an equation which consists various order derivative is called differential equation. Now we define linear differential equation. What is the meaning of linear differential equation, or when we said a differential equation is linear? So linear differential equation means a differential equation is said to be linear if the dependent variable, generally we write y, that if the dependent variable and its derivative occur in first degree only, that is the dependent variable and its all derivative occur in the differential equation has power 1. Further, there is no multiplication term of dependent variable and its derivative. So a differential equation is said to be linear if the dependent variable and its all derivative occur in the differential equation has power 1 and there is no multiplication term of dependent variable and its derivative. For example, this is a differential equation, dependent variable y power 1, first derivative dy by dx power 1, and there is no multiplication term of y and dy by dx, its derivative. So this is linear differential equation of first order. In this example, this is a differential equation. Now dependent variable y power 1, first derivative dy by dx power 1, second derivative d2y by dx2 power 1. So dependent variable and its all derivative has power 1 and there is no multiplication term of y and its derivative. So this is again a linear differential equation. But same time, in this example, this is differential equation, but here dy by dx power 1, d2y by dx2 power 1, but here dependent variable y multiplied by second order derivative, so this is not a linear differential equation. And Similarly, in this example, in this differential equation, here we get multiplication term of y and its derivative. So these are examples of non-linear differential equation. So a differential equation is linear if the dependent variable and its all derivative occur in first degree only, and further there is no multiplication term of dependent variable and its derivative. Now we define linear differential equation with constant coefficient. Linear differential equation with constant coefficient. In short, we write LDECC. So, what is linear differential equation with constant coefficient? So, definition is a higher order linear differential equation. Higher order means the order of differential equation must be more than 1, and further the differential equation must be linear. So a higher order linear differential equation in which the coefficient of dependent variable and its derivative, the coefficient of dependent variable y and its all derivative are constant, then the higher order linear differential equation is called linear differential equation with constant coefficient. So in a higher order linear differential equation, if the coefficient of dependent variable and its all derivatives are constant, then the equation is called linear differential equation with constant coefficient. So what is the most general form of LDCC of order n? So we write P0 and the derivative of y dn y by dxn plus P1 n minus 1 order derivative dn minus 1 y by dxn minus 1 plus P2 n minus 2 order derivative of y dn minus 2 y by dxn minus 2 plus so on plus Pn y equal to qx, where P0, P1, P2 and so on Pn are constant and the qx is function of independent variable x only. So this is the most general form of a linear differential equation with constant coefficient. Clearly this is a differential equation. This is linear because the power of dependent variable y and its all derivatives are 1, and further there is no multiplication term of dependent variable y and its derivative. So this is a linear differential equation, and also the coefficient of each derivative P0, P1, P2, these are constant. So by definition this equation is a linear differential equation with constant coefficient. For a linear differential equation, this part qx right hand side which not contain derivatives is called non-homogeneous part of the differential equation, and the left hand side which consists of derivative and dependent variable, this is called homogeneous part of the differential equation. Now we express this LDCC in symbolic form. So if the symbol D, capital D, stand for differentiation of y, like dy by dx, then we write dy. This d stand for derivative d by dx. d2y by dx2 we express d square of y. d3y by dx3 we express as d cube y, and etc. so on. Then the equation first can be expressed as P0, this is dny, Then P1, this is dn minus 1y plus P2 dn minus 2y plus so on Pny, and then we take y common is equal to Qx. So we express the given LDCC in symbolic form D. And further we write this expression contains constant and derivative D. So we write function of D y equal to Qx. So we can express the linear differential equation with constant coefficient in derivative symbol D also. For example, d2y by dx2 plus 3dy by dx plus 5y equal to e power x. So this is a differential equation. This is linear because dependent variable y power 1, dy by dx power 1, d2y by dx2 power 1, and there is no multiplication term of y and its derivative. So linear differential equation with constant coefficient. The coefficient of y is 5, constant. Coefficient of first derivative dy by dx is 3, constant, and the coefficient of second order derivative d2y by dx2 is 1, constant. So this is a linear differential equation with constant coefficient. Now we express this equation in the derivative symbol D. So this is d2y or d square y plus 3 constant as it is. This is dy, capital Dy, plus 5y, then y is common, then we have d square plus 3d plus 5y equal to e power x. Also, in this linear differential equation with constant coefficient, this can be expressed as d power 4y plus 3 constant as it is. d2y by dx2 we express as d square y plus y, and then y common, then we have d4 plus 3d square plus 1y equal to sin x. Similarly, here d3y by dx3 plus 2 d2y by dx2 minus dy by dx plus 3y equal to x square. So clearly this is linear differential equation with constant coefficient. So d cube y by dx cube, we write d cube y plus 2 d2y by dx2, we write d square y minus dy by dx, we write capital Dy plus 3y, then we take y common, then we have d cube plus 2d square minus d plus 3y equal to x square. So this is how we can express a linear differential equation with constant coefficient in form of symbolic derivative D. Now we discuss about the solution of a linear differential equation with constant coefficient. So the complete solution of a linear differential equation with constant coefficient whose dependent variable y is given by y equal to complementary function plus particular integral. So the solution of LDCC consists to two parts, complementary function plus particular integral. So y equal to complementary function plus particular integral. In short, we write the complete solution of LDCC is y equal to CF complementary function plus particular integral Pi. So y equal to CF plus Pi is the solution of an LDCC. Now, what about complementary function? The homogeneous solution of a differential equation LDCC, which consists of number of arbitrary constant equal to the order of differential equation, is complementary function. This is basically the solution of homogeneous part only. The complementary function is the solution of LDCC when the non-homogeneous part Qx is 0. So the solution of homogeneous part of LDCC is called complementary function, and this complementary function consists the arbitrary constants whose number is equal to the order of differential equation. Suppose the given LDCC is of second order, then complementary function consists two arbitrary constants C1 and C2. And for third order LDCC, the complementary function consists of three arbitrary constants C1, C2 and C3. So the complementary function is the solution of homogeneous part of the given LDCC. Now the particular integral is the non-homogeneous solution of the differential equation LDCC. The non-homogeneous solution of a differential equation which not contain any constant is called particular integral. So when we consider the non-homogeneous part Qx, then the solution of LDCC which not contain any arbitrary constant is called particular integral. So CF is the solution of homogeneous part only, and Pi is the non-homogeneous solution of the given LDCC. So these are the complementary function and particular integral, and complete solution of an LDCC is y equal to Cf plus Pi. Here we note that if the non-homogeneous part of LDCC, that is Qx, is 0, if the non-homogeneous part of the linear differential equation with constant coefficient, which we denoted by Qx, the right hand side, is 0, then the particular integral is also 0. Now we discuss how to find complementary function of a linear differential equation with constant coefficient. So let the given LDCC is function of dy equal to Qx. We expressed earlier in this form an LDCC. So let the given LDCC is function of dy equal to Qx. Then to find complementary function, to find CF, we write the auxiliary equation which is given by, so first we have to write the auxiliary equation, and which can be obtained by replacing d equal to m. In this function of d expression, we replace d by m and put equal to 0, then we get auxiliary equation. So auxiliary equation is function of m equal to 0. Now complementary functions depends on the root of this auxiliary equation. So complementary function depends upon the nature of the roots of auxiliary equation. Now we discuss 4 different cases for the complementary function based on the nature of roots of auxiliary equation. So case first, when the roots of auxiliary equations are real and distinct. Suppose the roots of auxiliary equation are real, that is they not contain iota, and further all the roots are different, no repeated root. So when the roots of auxiliary equations are real and distinct, so let the roots of auxiliary equation function of m equal to 0 are m equal to m1, m2, m3, so on mn. So these are the real and distinct roots of the auxiliary equation. Then we write CF. CF is given by C1 e power m1 into x. m1 is the first root. So C1 e power m1x plus C2 e power second root m2 into x. So plus C2 e power m2x plus C3 e power m3x and plus so on Cn into e power mnx. So this is how we write the complementary function of given LDCC when the roots of auxiliary equation fm equal to 0, function of m equal to 0 are real and distinct. All roots are real, not contain iota, and further all roots are different, there are no repeated roots, then CF is simply C1 e power m1x plus C2 e power m2x plus C3 e power m3x plus so on Cn e power mnx. Here C1, C2, C3, these are arbitrary constants. Now case second, when the roots of auxiliary equations are real but repeated. So case 2 is when the roots of auxiliary equation are real and repeated. Suppose the roots of auxiliary equation are m equal to m, first root is m, second root is also m, third root is m3, fourth root is m4 and so on. So here roots are real but the two roots are repeat, same value. Then the CF is given by, we write this repeated root simultaneously as C1 plus C2x e power mx. Together we give the complementary function part of repeated root as C1 plus C2x e power mx. Then other roots are different. So same way we write next constant C3 e power m3x plus C4 e power m4x and so on. So if two roots are repeat, then CF is given by C1 plus C2x e power mx plus for different roots same process C3 e power m3x plus C4 e power m4x and so on. In same case, if three roots are repeat, like the roots of auxiliary equations m are m, second root is m, third root is m, and then we have different root m4, m5 and so on. In this case, we write CF is, we together write the complementary functions for three repeated root as C1 plus C2x plus C3x square, then multiplied by e power mx. So this is complementary function part for three repeated root C1 plus C2x plus C3x square multiplied by e power mx, plus then roots is different, we write C4 e power m4x plus C5 e power m5x and so on. So for two repeated root, two constant together, for three repeated root, three constant together. Similarly, if there are four root repeated, then we write C1 plus C2x plus C3x square plus C4x cube multiplied by e power mx. So this is the way we write complementary function for real and repeated root. Now case third is when the roots of auxiliary equations are complex. Suppose the roots of auxiliary equation are alpha 1 plus minus iota beta 1, two complex root. Other two roots are alpha 2 plus minus iota beta 2 and so on. So we have four complex roots in form of alpha plus minus iota beta. In that case, the CF is given by, for these two complex root alpha 1 plus minus iota beta 1, we write e raised to alpha 1x. Alpha 1 is the real part, e power alpha 1x multiplied by C1 cos beta 1, the imaginary part, coefficient of iota. So C1 cos beta 1x plus C2 sin beta 1x, plus for these two complex root we add the CF e power alpha 2x, the real part, so e power alpha 2x multiplied by C3 cos beta 2x plus C4 sin beta 2x. Beta 2 is the imaginary part of coefficient of iota. So e power alpha 1x C1 cos beta 1x plus C2 sin beta 1x plus e power alpha 2x C3 cos beta 2x plus C4 sin beta 2x. So in case of complex roots, this is the process to write complementary function. And finally, case 4, when the roots of auxiliary equations are complex and repeated. Suppose the roots of auxiliary equations are alpha plus minus iota beta, and other two roots are alpha plus minus iota beta. So here the roots are complex but repeated, alpha plus iota beta, and here we get alpha plus iota beta. Other two repeated roots are alpha minus iota beta, and from here we get alpha minus iota beta. So roots are complex and repeated. In that case, complementary function can be written as e power alpha, the real part, e power alpha x, c1 plus c2 x cos beta x plus c3 plus c4 x sin beta x. So similarly, in the real root we write for repeated roots. So in complex root we use same type of constant here, e power alpha x. For two repeated root, c1 plus c2 x cos beta x plus c3 plus c4 sin beta x. So these are the four cases based on 4 cases to express complementary function based on the nature of roots of auxiliary equations. Now we discuss 4 examples on these 4 cases, how practically we write the complementary function. So our first example is solve d2y by dx2 plus 5dy by dx plus 4y equal to 0. So first we check whether it is linear differential equation with constant coefficient or not. This is higher order differential equation. Now since y power 1, dy by dx power 1 and d2y by dx2 power 1, and further there is no multiplication term of y and its derivative, therefore it is linear differential equation. Also the coefficient of y is 4 constant, its first derivative dy by dx coefficient 5 constant, and the coefficient of second derivative d2y by dx2 is 1 constant. So the coefficient of dependent variables and its all derivatives are constant, therefore it is a linear differential equation with constant coefficient. So given equation is LDECC, and therefore its solution is y equal to CF plus PI. Y is dependent variable, so solution is y equal to CF plus PI. Here the non-homogeneous part, the right hand side, Qx is 0, therefore Pi is 0. So since Qx is 0, therefore we have Pi is 0, and hence y equal to CF is the only solution. Now we write the given differential equation in symbolic derivative operator D. So in place of d2y by dx2 we write d square, capital D square y plus 5. In place of dy by dx we write capital Dy plus 4y, and then we take y common, then the given equation become d square plus 5d plus 4y equal to 0. Now to find CF we write auxiliary equation, and which can be obtained by simply d replaced by m and equating to 0. So we have the auxiliary equation is m square plus 5m plus 4 equal to 0. Now here the factor of this quadratic equation are m plus 1 into m plus 4 equal to 0. Then we get the value of m. From here we get value of m is minus 1, and from here we get the value of m is minus 4. So the roots of auxiliary equation are minus 1 and minus 4. So both roots are real and both roots are different. So roots are real and distinct. In that case we know the CF is given by C1 e power m1x plus C2 e power m2x. So y equal to CF is the solution, and CF is C1 e power m1 is minus 1, so minus 1x plus C2 e power m2. m2 is minus 4, so minus 4x. So this is the solution of given LDECC. Next example is solve d3y by dx3 minus 3 d2y by dx2 plus 4y equal to 0. So this is a differential equation. Further, it is linear because y power 1, d2y by dx2 power 1 and d3y by dx3 power 1. And there is no multiplication term of y and its derivative. So this is linear differential equation. Further, the coefficient of y and its all derivatives are constant. 4, minus 3 and 1 are constant. Therefore, this is linear differential equation with constant coefficient. So given equation is LDECC and therefore its solution is what? Y equal to CF plus PI. Now first we write the given equation in form of symbolic derivative capital D. So this is d cube by capital D cube by minus this is minus 3 into this is what? D capital D square y plus 4y, and then we take y common, then we get d cube minus 3d square plus 4y equal to 0. Here the non-homogeneous part of given LDCC, that is the right hand side, qx is 0, therefore pi is 0. Now pi is 0, therefore y equal to cf is the solution, and to find cf we write the auxiliary equation, which can be obtained by simply d replaced by m and equating to 0. Then the auxiliary equation is m cube minus 3m square plus 4 equal to 0. So this is the auxiliary equation and this is a cubic equation. So we have 3 values of m, but factor is not possible here. So we find one root by trial. If we put m equal to minus 1, then minus 1, here minus 3, minus 4 plus 4 is 0. So equation satisfied at m equal to minus 1. So m equal to minus 1 is one of the root of this auxiliary equation, and therefore m plus 1 is one of the factor. Now we divide this equation by the factor m plus 1, then complete division, m square minus 4m plus 4 times, and therefore this expression is equal to product of these two. So given auxiliary equation can be expressed as m plus 1 into m square minus 4m plus 4 equal to 0. Further, m square minus 4m plus 4, this is what? M minus 2 whole square. So we get m plus 1 into m minus 2 whole square. So from here we get m equal to minus 1, and from here we get m equal to 2, m minus 2 into m minus 2. So we get the roots of auxiliary equations are m equal to minus 1 and 2 root from here m equal to 2 and 2. So roots are real and repeated. Therefore we write the CF, which is the solution. Y equal to CF is solution because pi is 0. So we write this is different root. So we write C1 e power m1x, so minus 1x, plus for 2 repeated root we write C2 plus C3x e power 2x. So this is the example on real and repeated root. Next example is solve d4y by dx4 plus a4y equal to 0. So this is differential equation. Further it is linear because y power 1 and d4y by dx4 power 1, and there is no multiplication term of y and its derivative. So linear differential equation. Also constant coefficient because the coefficient of y is a power 4 constant and its derivative d4y by dx4 coefficient is 1 constant. So given equation is LDECC, linear differential equation with constant coefficient, and therefore its solution is y equal to CF plus Pi. Now the homogeneous part, the non-homogeneous part of this equation, Qx is 0, therefore Pi is 0, and hence y equal to CF is the solution. Now we write this linear differential equation with constant coefficient in form of differential operator capital D. So this is what? This is d4y plus a4y equal to 0. So y common, we get d4 plus a4y equal to 0. Now to find CF, we write the auxiliary equation, and which can be obtained by d replaced by m and then equating to 0. So the auxiliary equation is m power 4 plus a power 4 equal to 0. So this is a biquadratic equation, gives 4 values of m, and further the factor is not possible. So we write this equation as adding 2a square m square and subtracting 2a square m square. We get m power 4 plus 2a square m square we add plus a power 4 and subtract 2a square m square. Now this part is what? This is whole square of m square plus a square. So we write m square plus a square whole square, and this is what? Root 2am whole square equal to 0. Now a square minus b square is what? A plus b into a minus b. So we write a m square plus a square plus b root 2am into a minus b. So a is m square plus a square minus b, so minus root 2am equal to 0. So these are two quadratic factor of this biquadratic equation. Now to find the values of m, we use discriminant method, minus b plus minus b square minus 4ac by twice a. So this factor is 0 or this factor is 0. Now from here we get m equal to minus b. So b is what? Root 2a. So minus root 2a plus minus b square. B square is root 2a whole square, which is 2a square minus 4a. A is 1, coefficient of m square. A is 1 and c is a square upon twice a. So 2a is 1 here. And similarly from here we get minus b. So b is minus root 2a. So minus minus plus root 2a plus minus b square. So root 2a square is 2a square minus 4a is 1 and c is a square. So minus 4a square by twice a is 1. So 2a square minus 4a square is minus 2a square, and square root of minus 2a square is iota root 2a by 2, and similarly here root of minus is iota and 2 is root 2 and a square root is a. We get this. Now separating the LCM, we get with the values of m. Here root 2 by 2 is 1 upon root 2a plus minus iota. Here root 2 by 2 is 1 upon root 2a, comma here root 2 upon 2 is 1 upon root 2a plus minus iota. Root 2 upon 2 is 1 upon root 2a. So roots are these are the 4 roots, and roots are complex: alpha plus minus iota beta, alpha plus minus iota beta. Here alpha is minus 1 upon root 2a, then here alpha is plus 1 upon root 2a. So roots are complex and different. So in case of complex root, we know how to write the complementary function. So y equal to CF is solution, and CF is e power alpha. So here alpha is minus 1 upon root 2a. So e power alpha x. C1 cos beta. Beta is 1 upon root 2a. Iota beta. So 1 upon root 2a x. C1 cos beta x. Plus C2 sin beta. Beta is 1 upon root 2a. So C2 sin beta x. And for these two root, we write plus e power alpha x. So here alpha is 1 upon root 2a, so e power alpha x. Now C1, C2, then C3 cos beta. Here beta is 1 upon root 2a, so cos beta x, plus C4 sin beta x. Beta is 1 upon root 2a. So this is how we write the complementary function for complex roots. Now the last example is solve d power 4 plus 2d cube plus 3d square plus 2d plus 1y equal to 0. So this equation is clearly written in form of differential operator capital D, and therefore this is LDCC. Given equation is LDCC. We can check this equation is d4y by dx4 plus 2 d3y by dx3 plus 3 d2y by dx2 plus 2 dy by dx plus y equal to 0. So this is linear differential equation with constant coefficient, and therefore its solution is y equal to cf plus pi. Further, qx is 0, therefore pi is 0. Hence y equal to cf is the solution. Qx is 0, therefore pi is 0. Now to find cf, we have to write auxiliary equation, and which can be obtained by simply d replaced by m and equating to 0. So the auxiliary equation is m power 4 plus 2m cube plus 3m square plus 2m plus 1 equal to 0. Now this is whole square of m square plus m plus 1. M square plus m plus 1 whole square. We expand m square plus m plus 1 whole square, we get this result. Now there are two parts, m square plus m plus 1 into m square plus m plus 1 equal to 0. So we get either m square plus m plus 1 is 0 or m square plus m plus 1 is 0. Now quadratic expression. So root can be obtained by discriminant rule, minus b plus minus b square minus 4ac by twice a. So we get m is equal to minus b. So b is 1, coefficient of m. So minus 1 plus minus b square, 1 square is 1, minus 4 a into c. So a is 1 and c is 1. So we get minus 4 upon twice a. Here same, we get minus b plus minus b square minus 4ac. So a and c are 1 upon 2. This is minus 3. So square root of minus 3 is iota root 3, and then we separate the LCM. Then we get m equal to minus 1 by 2 plus minus iota root 3 by 2. Here minus 1 by 2 plus minus iota root 3 by 2. So roots are complex, but alpha and beta for both are same. So these are complex and repeated root. For both root, alpha is minus 1 by 2 and beta is root 3 by 2. So two roots are repeated in the pair of 2, 2. So in case of complex repeated root, CF is given by e power alpha x, alpha is minus 1 by 2x, into C1 plus C2x for repeated root, C1 plus C2x cos beta, beta is root 3 by 2, so cos beta x, plus C3 plus C4 x sin beta x, so beta is root 3 by 2 x. So this is the solution of given linear differential equation with constant coefficient, and this is the example where the complex roots are repeated. In next video we will discuss the cases of PI, how to find particular integral. So see you in next video. Thank you.